Hello, this is Geometry, Lesson 4-2, Isosceles and Equilateral Triangles. In this lesson, we'll apply theorems about isosceles and equilateral triangles to solve problems. Let's look at explore and reason. Cut out a triangle with two sides of equal length from a sheet of paper and label its sides, its angles 1, 2, and 3. Trace the outline of your triangle on another sheet of paper and label the angles. Okay, so if you cut out a triangle and then you trace it on the outside, okay, and then you label the angles, in how many different ways can you flip, slide, or turn the triangle so that it fits exactly on the outline? Okay. You flip it, it's a reflection. You slide, it's a translation. If you turn, it's a rotation. Okay, so no matter which way you flip, it's gonna fit the outline if you flip it on the vertical line. So like if you reflect it on the vertical line and you flip it horizontally, right? But you cannot turn it, like rotate it. Wait. Yes, you cannot turn it or slide it and still have it fit in the outline. When you have angles labeled, right? And you can trace it. If you slide it, of course, it's not going to fit the outline. When you turn it, there are points where triangle's not going to fit the outline throughout the whole rotation, right? Maybe until angle 1 goes to angle 3 or 3 to 2. You have a triangle that fits the outline maybe like 3 times of the whole rotation, but yeah. So you can say the triangle fits the outline no matter which way it's flipped, but it can't be turned or slid to fit the outline all the time. Okay, how do the angles and sides of the outline correspond to the angles and sides of the triangle? How do they correspond? The location of angle 1 and the bottom of triangle are the same on the outline, right? The locations of 2 and 3 on the angle are switched on the outline, front and back, right? The locations of the left and right sides on the triangles are switched on the outline. Okay, so yeah, your bottom side is still the bottom side, but left and right side becomes flipped. So let's write part B here. Okay, part C. How would you answer to part A? Change if all 3 sides of the triangle were of equal length. If all the sides were equal length, if this is an equilateral triangle, it could be turned by 120 degrees and 140 degrees and still fit in the outline. Okay, if it's not an equilateral triangle, it can't be turned at all. Okay. could be turned by 120 degrees and 240 degrees to fit the outline. And it could be flipped across 3 lines and still fit. Also, flip 3 lines. Okay, so in this lesson, let's think about how the side lengths and angle measures are related in isosceles triangles and equilateral triangles. Okay. So this was an an isosceles triangle because there are only 2 sides that are equilateral. All right, but then if this was an equilateral triangle, if all 3 sides were congruent, then you get a little bit more symmetry and transformations that can map onto itself. Let's look at example 1. Understand angles of isosceles triangles. How are the base angles of an isosceles triangle related? Okay, so if you look at an isosceles triangles ABC, we know that 2 sides are equal. Because the sides are equal, there's going to be a reflection. There's going to be a rigid motion that maps BC to BA because they're congruent, right? So if you draw an angle bisector here through the angle CBA, you get a reflection line. Okay, so these triangles are congruent. We're going to copy isosceles ABC, reflect the triangle across line BC to create image CBA, prime, prime, prime. What rigid motion maps CBA onto ABC? Can you use this to show that A is congruent to C? Okay. So if we reflect the triangle across line BC, to create image CBA. Okay. It's not super accurate, but if that's A prime, B prime, and C prime. Okay. What rigid motion maps C prime, B prime, A prime onto ABC? Can you use this to show that A and C are congruent? Okay. Of course, we reflected it, so reflection's gonna map it, but can we use another transformation? CBA, because the points CBA needs to map onto ABC. So notice your reflection needs to map ABC to A prime, B prime, C prime. But in order to have CBA mapping to ABC, you need to rotate it, right? Rotate it about point B so that you can go back to, right? So you will get an hexagon, right? So if you rotate it here, or you rotate it the other way, you will map C prime to A, and B prime to B, and then A prime to C. Yeah, so you need to pay attention to the points and the corresponding points. The rotation about point B. So angle A should be congruent to angle C because it's a rotation is a rigid motion. Okay. So is a composition of transformations that maps ABC onto CBA the only possible composition? No, there are other transformations that are equivalent to this composition, such as reflecting over a horizontal line through the vertex angle and then rotating 180 degrees about the vertex angle. Okay, like we learned in the last topic, there are compositions of transformations that can map one transformation. So look at theorem 4-1, isosceles triangle theorem and the converse. If two sides of a triangle are congruent, then the angles opposite those sides are congruent. Just like this. If two angles of a triangle are congruent, then the sides opposite those angles are congruent. So if these two angles are congruent, these two are congruent. If those two sides are congruent, these two are congruent. Okay, the opposite sides, opposite angles. Example 2, use isosceles triangle theorem. An architect is designing a community park between North First Street and South First Street. The pathways on either side of the pool will be equal in length and will provide effective access and circulation around the pool. So these two are equal length. Okay, to protect the landscaping and to minimize erosion, the architect will place a triangular section of triangular cobblestones at the corners along Park Plaza. What angle measure should the architect specify for the corners in their design? If this is 50 degrees, and by using the theorem, right, the isosceles triangle theorem, if these two sides, if opposite sides are congruent, opposite angles should also be congruent. We know that the triangle has 180 degrees total. So subtract that by 50, and that's how much angle we have for both, divided by 2, so that we get an equal angle for angles E and F, which is 65. So the landscape architect should specify that the angles at the corners measure 65. So using the same theorem, let's figure out the values of x on your try question. Figure out, work, and come back when you're ready. So by the theorem, if two sides here are congruent, we know that this is also 28. And so using the triangle sum theorem, 180 minus 56 divided by 2 should equal to 5x plus 9. Does that make sense? You subtract these two. So this is from 28 times 2. Okay. Wait, not divided by 2. Sorry. 180 minus 56 should equal to 5x plus 9. Okay. And so if you solve for x, what do you get? Okay, you get 124 degrees here, 5x plus 9, and then subtract 9 on both sides. Okay, and then you only have 5x on this side, and you have 115. 115 divided by 5 is 23, right? So x is 23. Okay, what about B? We know these two angles must be the same. So negative 4x plus 9 should equal to 8x minus 3. Solve for x. We get 8x plus 4x here and 9 plus 3 here, because if you add 3 on both sides and add 4x on both sides, you get this. And we have like terms. And now add the like terms. 12 is equal to 12x. Divide both sides by 12 and x is equal to 1. Okay? So this only works for isosceles triangles. Let's look at example 3. We're going to use the converse of the isosceles triangle theorem. Remember that converse is the opposite of the theorem. So if then statement switches. Okay, what are the lengths of all three sides of the triangle? So use the theorem backwards. If we have all these angles, right, all these lengths, And we know that two angles are the same measurement. We know that these two sides must be equal to each other, right? Then you can say x plus 20 should equal to 8x over 3. Solve for x, x is 12. And now that you know x, substitute that in here. 6 times 12 minus 12 is your PQ. And then plug x into PR and QR and figure out all their lengths. 32, 60, and 32. Okay? Let's use the same theorem, the converse of the same theorem to answer this try question. Come back when you're ready. Okay, so here we know these two angles are congruent, which means these two sides are the opposite sides that are congruent. And this is the base. Okay, so 8x minus 1 should be 4x plus 5. Solve for x to get 4x is equal to, you subtract 4x here, and then you got 4x. Then you add 1 from 5, you get 6. So x is equal to 6 over 4. Simplify your fraction, 3 over 2. Okay, so x is 3 over 2, or 1.5. What are the lengths of all three sides? You solve it one by one. 2 times 3 over 2 plus 11. And then 8 times 3 over 2 minus 1. And then 4 times 3 over 2 plus 5. Okay, and that's 6 plus 5, 11. And then this is 3 plus 11, which is 14. And then that is 12 minus 1, which is 11. Okay, so we got 11, 11, and 14. Okay, let's look at theorem 4-2. If a line or line segment bisects the vertex angle of an isosceles triangle, then it is also the perpendicular bisector of the opposite side. So we still have an isosceles triangle. If A, B, and BC are congruent and the angles ABD and CBD are equal to each other, then we know the other sides should also be equal, and it should be the BD, line BD is perpendicular to the other side. Okay, so it's a perpendicular bisector. Okay. So using that, keeping that in mind, let's look at example 4. Use perpendicular bisectors to solve problems. A prefabricated house is delivered to a fountain in 2 symmetric halves that are assembled on site. Along the planned route to the site, the truck must pass under a bridge that has a clearance height of 17 feet. Should a trucker plan a different route for delivering the house? Explain. So we got all these dimensions here. We can see that these two sides are equal in length. And we can see that these two angles are equal in length. So you know, using the theorem that we just looked at, 4.2, we know that if this is D, BD is a perpendicular bisector, right? So this is going to be perpendicular as well. All right. So you can use a diagram to represent the roof, and you see that the height here is going to be a perpendicular bisector, BD. And knowing that this 14 feet, 16 feet, right? They're all going to be the same here. You can use Pythagorean theorem to find the height h. This is the hypotenuse, okay? And that's A and that's B if you have a triangle. This h represents height, and so yeah, this is the hypotenuse. And that's A and that's B. So your hypotenuse or your height is going to be part of A. You know that A squared plus B squared is equal to hypotenuse squared. Okay, so then h squared plus 14 squared is equal to 16 squared. Your h is about 7.7. The house is approximately 17.7 feet tall. So the total height that the truck must clear is greater than 17.7 feet. Okay, using this one, 10, that's a 10 feet height. Okay, so the trucker should plan a different route to the site. Let's use the figure shown. What is the measure of angle RSQ? And what is PR. What is the length of PR? Come back for answers when you are ready. Okay, measure of angle RSQ should be the same as this angle, but we know this is an equilateral triangle because these two sides are congruent, so that's also 31. And so 180 minus 31 is equal to the whole angle, right? And then you divide it by 2 to get angle of RSQ. Okay, so that is 59 degrees. What is the length of PR? If this is a perpendicular bisector, because you have the same angle here and the same side length, we know that these two side lengths are going to be equal, right? So that's 4, and PR is the total side length of the base, which is 4 plus 4, 8. Okay? So next page, equilateral triangles.